Hey guys, welcome back to part two. This video is going to be a little bit more practice. We're going to do a recap, I think one or two practices, and then we should be okay. Like I said, let's just recap what we've done previously. So, we learned about equilibrium. We said that equilibrium occurs when the rate of our forward reaction equals the rate of our reverse reaction. In layman terms, that means that the speed of our forward reaction will equal to the speed of our reverse reaction. Now, in terms of concentration for equilibrium, concentration is constant, meaning it is present within the reaction, but it is neither equal. It is not equal. Now, there's three types of equilibrium. There is phase equilibrium. That's when the rate of the melting equals the rate of the freezing. Then we have solution equilibrium. That's when the rate of the dissolving is equal to the rate of the crystallization. Think of rock candy. And then we have chemical equilibrium, which is the rate of the forward equaling the rate of the reverse. Meaning the speed of which we are breaking bonds equals the speed of which we are forming bonds. Now, the same way you go through stress is the same way chemical reactions go through stress as well. So, the stresses that chemical reactions go through are concentration, temperature, and pressure for gases only. Now, what Le Chatelier's principle says is that while this chemical reaction might be under stress, it will shift to accommodate that stress and reach a new equilibrium. Let me state that again. While the chemical reaction might be at stress, it will shift to accommodate that stress and reach a new equilibrium. So at the end of this, we just want a new equilibrium. So let's recap our stresses and the impacts they have in a chemical equation, and then we can go on to our practice. So we have concentration. When we increase concentration, we shift away. By shifting away, we're going to increase the concentration on the new side that we shifted on, and we're going to decrease the concentration for the other substances on the old side. When we decrease concentration, we stay on the same side. We replace what we take, and concentration will increase for this side that I'm on, and decrease for the other substances on the other side. Same thing applies to so like I said, the same thing applies for temperature. So let me quickly go through this. So for temperature, when we increase temperature, we're going to shift away. By shifting away, concentration will increase on the new side where the temperature shifted to, and decrease from the others for the other substances on the old side. So wherever temperature moved to is going to help that side, and in comparison, the old side will look like it decreased. When we decrease temperature, we're going to stay on the side. We're going to stay on the side that we removed it from. Whatever we take, we're going to replace. So that means that side concentration will increase, and the other side that doesn't have temperature would decrease in comparison. Then we have pressure. Remember, pressure only affects gases only. So for pressure, when we increase pressure, we're going to shift to the side with the least. And what I mean by the least, I mean the least amount of molecules. So to determine the least amount of molecules, you're going to add up the coefficient on your reactive side and get one number. You're going to add up the coefficients on your product side and get a number. Those are your molecules. So you're going to go to when we increase pressure, you're going to go to the side with the least amount, and you're going to increase the concentration of the substances on that side. The other side would decrease as default. And when you decrease pressure, you're going to shift to the side with the most, and you're going to increase that side because that's where pressure is. You're going to increase the concentration on that side, and the side that doesn't have the shift of pressure, that side would decrease as a default. Now, I'm going to go ahead. This is my little cheat sheet that I'm going to use to help me do this next practice. So here we have this practice, and this is a famous chemical equation that I cannot remember at this exact moment. So we have N2 gas plus 3H2 gas at equilibrium with 2NH3 plus 22.0 KCl. Now, by looking at this chemical reaction, I can tell that 22.0 KCl, that is my energy, right? KCl, kilocalories. That is my energy. And because it is on my product side, I can tell you that this reaction off the bat is an exothermic reaction. So, always be able to tell what type of reaction it is based on the placement of energy. Now, let's go ahead and just deal with this shift. I'm going to be writing it in, so it might take a little bit of delay. But we should be okay. So let's get started. So, if we add N2, we're going to shift away because we're doing an increase. So when we add N2, we're going to shift away. So that means we're going to go towards our product side, right? And because we shifted away from our reactant side, that means the concentration of NH3 is now going to increase. Basically, I've added more particles of NH3 and thus I'm increasing its concentration. But as a default, the concentration of H2 being on my other side will decrease. Not that it technically decreased, but in comparison to everything's increase, it looks like it has. Now, when we add H2 is right here. H2 is on our reactant side. So when we add H2, it's going to shift away from it. It's going to shift away. So when it shifts away, it's going to go towards our product side. And because it went towards our product side, once again, NH3's concentration is going to increase. But N2's concentration, and compared to the other increases, is going to look like it decreased. So now let's add NH3. NH3 is on our product side. So when I add NH3, I'm going to shift towards that's right, my reactant side. So when I shift towards my reactant side, anything on my reactant side is going to benefit from that shift. So that means my concentration of N2 is going to increase. And my concentration of H2 is also going to increase. Don't make fun of my arrows. I'm trying. All right, so let's go ahead. So that's dealing with the increases. So now let's deal with the decreases. Now I'm going to remove H2. Remember, anything that I remove, I must put back. So if I remove N2, I have to put it back. That means I have to stay on my reactant side. And because I'm staying on my reactant side, the concentration of H2 will increase as default. And the concentration of NH3 will decrease because I took away some of the N2. So if I took some of the N2 away, even though I'm shifting to accommodate it, I still have less N2 to make NH3. So let's work with removing H2. So if we remove H2, remember, whatever I take, I must put back. So that means I'm staying on my reactant side. And then the concentration of N2 is going to look like it's going to increase. Not look like it is. So it's going to increase. But the concentration of NH3 is going to decrease because now I have less H2 to make NH3. Now, I'm going to go ahead and shift. We're going to remove NH3. So if we remove NH3, NH3 is on our product side. When we remove NH3, we're going to put it back. So we're going to stay on our product side. Now, because we stayed on our product side, the concentration of N2 and H2 are going to decrease because the NH3 is getting all the assistance. So that was concentration. Number 7 has to do with temperature. So temperature, right, we said temperature is on our product side. So if we increase our temperature, we're going to shift away from the increase. So we're going to go back, we're going to go to our reactant side. We're going to shift away from our products and go to our reactant side. Now, wherever we shift it to, we're helping that side more. So meaning the concentration of anything on my reactant side is going to increase. So N2 is going to increase. H2 will also increase, and NH3 will decrease. Now we have this increase because by placing temperature at in the reactant side, we're causing more collisions, meaning more collisions, they're going to react a little bit more. Now, when we decrease temperature, remember, wherever we take, we put back. So when we're decreasing temperature, we're going to put it right back where it was. So we're going to put it in the product side. And it's going to help anything on the product side. So because N2 is not on our product side, its concentration is going to decrease. Because H2 is not on our product side, its concentration is going to decrease. And because NH3 is on our product side, its concentration is going to increase. All right. So now we're dealing with pressure for 9 and 10. Well, we have to pay attention to gases. Do we have gases? And it looks like we do. So we're now going to add up the molecules. Now, remember, just because there's nothing here does not mean that it does not have a coefficient. Its coefficient is 1. So in total, the reactant side has 1 plus 3. So it has 4 moles total on the reactant side. And our product side, we only have 2 of NH3. So we have 2 moles in total for our reactants, product side. So if we increase pressure, we're going to go to the side with the least amount. So which one has the least? 4 moles or 2? 2, correct. So that means we're going to shift towards our product side. Now, when we shift towards our product side, anything on our product side, we're going to increase its concentration. So NH3 has an increase in concentration. But H2 and N2, because they're on their reactant side, have a decrease in concentration. Right? Let's go ahead and work with number 10. If we decrease the pressure, we're going to go to the side with the most. So which one has the most? 4 or 2? Our reactants or our product? Our reactants has the most. So we're going to shift towards our reactants. And meaning when we shift towards our reactants, we're going to increase the concentration of all our reactants. So that means N2 is increased and H2 is increased. And that means the concentration of NH3 by default ends up decreasing. All right. So hopefully this helped you guys out. One thing that I know some of you were saying while we were in the Zoom session was, well, what if we have an equal amount of moles? Well, if you have an equal amount of moles, you have no shift. Remember, you must have a least and a most amount of moles. If you do not have that, there is no shift, meaning you are not going to be able to shift your pressure to the reactant side or the product side. All right. Now, go ahead, go onto Test Wizard, go onto Google Classroom and practice this out. Tomorrow on Zoom, we're going to practice this a little bit more. We have a lab based on this on Wednesday, so we're going to practice this out. We're going to make sure we all understand Le Chatelier's principle. All right, with that being said, I'll see you guys later tomorrow. If you have any questions, let me know through our chats, and I'll be more than happy to help you. Have a great day, guys, and be amazing. Stay safe.